Good morning, everybody. This is Kevin Renaud with Peerless. Thanks for joining us. Today is week 7 of our training session, our e-learning trainings, continuous level measurement with radar level transmitters, featuring Norm Ouimet from KROHNE. This is his second appearance. Again, there are a bunch of people still filing in, so we're just going to give him a few more seconds and we'll begin. All right, we're going to go ahead and get started. Once again, thank you. As usual, those of you that have been with us before, I do start to show by the geography of those in attendance. Today we have 13 states represented. So it is our biggest number. 26% of the states are represented today. Thank you. Industries are very broad and diverse as usual. So thank you again. Again, Peerless here in Buffalo, New York, been around 106 years, but we've become a trusted source for process components to keep plants operating safely and efficiently and projects running smoothly and on time. Our customer base out there is quite diverse and skilled, working on highly complex projects, and naturally we're quite proud of the role that we're allowed to play. Our 3 divisions, ProCore, consists of the OEM customers, custom engineered, packagers and skid builders, and our process group, more the MRO product, chemical, pharmaceutical, contractor, power, etc. And again, finally, our high temp fabrication division, where we do manufacture high temperature insulation product, refractory, and scientific surfaces. So Norm Ouimet is with us once again, District Manager for KROHNE. Thank you, Norm. And with him is Marty McLean. From our side of the house, we have Dan Morgan, we have Greg Barrell, and once again, me, Kevin Renaud, with business development. 2 weeks ago, actually, when Norm joined us, we learned that when he's not selling instruments, he's playing instruments in his band Backbeat, and he actually had produced a CD not long ago. So I did learn that Marty does like to play a little bit of backup vocals for Norm in these presentations, so I figured we should share something with him. He sent me his bio, and as they say, last impressions were first impressions. So the first thing he mentioned to me was that if I were to look in his 1982 high school yearbook, he would be voted the class clown. So I kept hearing that every sentence of his bio, I kept hearing class clown. So that's what we're leading with. So thank you, Marty, for being a part of this today as well. So with that, I am going to turn it over to Dan Morgan, who's going to cover some brief housekeeping notes, and we'll get started. Thanks again for joining us.
Thanks, Kevin. Yeah, and thanks again to everyone joining us. Just want to cover a few things for those of you that are maybe joining us for the first time here today. As Norm is going through his presentation today, it really does make the most sense if we're covering topics and answering questions that mean the most to you. So we really do want some engagement and some participation in the form of questions throughout the presentation. So you'll see the questions panel in your control panel tool. So please feel free at any point in the presentation to raise a question, and I will be keeping track of those and interjecting throughout Norm's presentation to make sure we get those questions answered for you. There's also going to be a couple of points throughout Norm's presentation where he's going to ask some questions, and if you feel you have the answer or would like to participate, feel free to toss an answer in through the questions panel. So look forward to some interaction there. And with that, I will now turn it over to Norm.
Okay, good morning, everyone, and thank you very much for being with us once again. Watching Kevin's little presentation at the beginning saying that Peerless is 106 years old, it reminded me that KROHNE is going to be 100 years old next year. So both of our companies have been around for quite a while. So today we're going to be talking about radar level transmitters. These are the topics we're going to cover: basics, different types, measurement principle, pros and cons, and then we're going to talk about the effective frequency a little bit in there. So what are we looking at? When we're doing a radar level measurement, it's based on time, right? The time required for a pulse to reflect an echo off of the medium that's being measured. Also, sometimes we're looking for a shift in frequency as well as a pulse that's being reflected back. And we're going to talk about the differences there as we go along. So then when that signal comes back, the transceiver is able to take that signal and process it and interpret where the level of the medium is within the vessel. So there are basically two types of radar level instruments. There's guided wave radar, okay, and if you look at right here, this red cylinder right here, this shows that with guided wave, we actually have a cable or a coaxial rod that guides the pulse signal down and back up. And that is more of a cylindrical shaped kind of signal. So then we have non-contact radar, which we'll also be talking about. The wave travels through the air. There is nothing that comes in contact with the medium. And that is more of a cone shaped, and that is this little bit darker, like blue-green area right here. And just as a comparison, ultrasonic, which has been around for a long, long time, you'll notice is also cone shaped, but has a much wider beam. Given the same distance and the same type of vessel, your radar, non-contact radar, will always have a smaller beam than your ultrasonic. And also we'll talk about a couple of other things along the way regarding that. So first we're covering the guided wave radar devices. Guided wave, also known as TDR, or time domain reflectometry. So basically what happens is we send a signal out, that signal is reflected back. Based on the length of time that it takes for that signal to come back, we are able to interpret via the electronics in the device where the level is at. This is a technology that was originally invented for detecting breaks in underground cables. So they would send a signal out, and let's say they knew the cable was 5,000 feet long. They send out this pulse, wait for it to come back. Now, if there was a break in the cable, you would get a reflection from where that break was. And the time of travel, they would be able to pinpoint pretty much exactly where that break was. If the break was at 3,000 feet, 2,000 feet, that way they didn't have to dig up the entire cable to find the break. They could just go dig in that one spot. So at some point, someone decided, hey, we can probably use this same technology to look at the level inside of a vessel, which is actually, how guided wave radar level devices came along. So basically, again, electromagnetic pulse emitted, guided along a probe, right? So we see here the pulse coming down. When it hits the medium, we get an echo back, and we look at the time of travel. Okay, so if we look at this, right, distance is calculated, again, transit time of the pulse, or what is also known as time of flight. So if you'll notice, watch the pulse going down, coming back, and then in this manner, we're able to determine where the level of the product is. So one of the big things with radar level devices, whether it be a guided wave or the non-contact, which we'll be covering later, is the dielectric constant of the material that we are trying to measure. Dielectric constant is going to determine how much reflectivity we're going to get from that material. So epsilon R is used as an abbreviation for dielectric constant. Sometimes though, you'll see just the lowercase k or dk for dielectric constant. Depends on which manufacturer's literature you're reading. They will use different abbreviations for the dielectric constant. Dielectric constant is simply a number. There is no actual engineering unit for dielectric constant. It's just a number. But if we look here at a range of products from hydrocarbons to aqueous solutions, you'll notice that the percentage of reflection goes up with the increase in dielectric constant. So if we're looking at an aqueous solution, we see a lot of reflectivity. Pretty easy stuff to measure. As we get down towards the hydrocarbons, it becomes more and more difficult to measure those products with a radar level device. Doesn't mean we can't do it. It just means that's going to be more difficult. Now, in some cases, if the dielectric is way, way too low, then we simply cannot use this technology. So again, it's a number, dielectric constant, the ability of a material to carry alternating current compared to the ability of a vacuum to carry alternating current. So they look at the difference between those two and they come up with a number, okay? We need to know this number in order to properly design a level measurement system that's going to be using this technology that we're talking about. Higher dielectric reflects more signal, lower dielectric reflects less signal. So just a quick look at some common materials, and you'll notice these are not all liquids. As we get down towards the bottom here, you'll notice glass beads, fly ash, cement, this being the powder form, not concrete, but cement. You'll notice that the dielectric is low, but we're still able to use these types of instruments in cement silos and, and give a very reliable and accurate measurement. So there are products not only for fluids, liquids, but there's also products for solids and powders. Guided wave radar devices, sometimes we can get as low as 1.1. Now notice I've got an asterisk there. This may require the use of something called TBF, or tank bottom following mode. Some devices are capable of this, and with tank bottom following, what happens is the signal travels first through the air, then through the medium, and reflects off the bottom of the tank. But what happens is, even though we're not getting enough reflection from the material itself, the speed of the signal slows down as it travels through the medium. So the device is intelligent enough to be able to measure the amount of time it took for the signal to travel at the higher speed through air, and then the amount of time that it was able to travel through the medium at a slowed down rate. And by being able to take a look at both of those values and do some math, it's able to give us our level within the vessel, even though we're not getting a whole lot of reflectivity from the material itself. Probe types. So probe types is very important when you're selecting a device, a guided wave radar device. So, there are single cables, double rods, coaxial, and all of these have their uses and have their applications. Now, the most efficient one is the coaxial probe. This is going to give you the best impedance, the highest sensitivity. If you can use the coaxial probe, that's your better way to go when you're doing a guided wave radar. However, they are more expensive, and depending on what the material is within that vessel, they may be subject to clogging. I mean, if this were a vessel full of corn syrup, this would not be a good probe for that. So then we go to the single rod. Of course, there's double rod in between there, which I haven't put a picture of. But the single rod is the most popular. It's the least expensive. However, it's the most difficult to set up. Works well, but you're going to be spending a little bit more time during the setup phase, during the startup and commissioning of the device. It's going to take you a little bit longer to get everything set just right, and to do the programming in the device to make it work properly. Signal and noise. So two things that we have to be aware of, okay? The signal, that is what we're looking for, the desired signal from the level surface. This is what's going to tell us where our level is within that vessel. Noise is anything else other than that. Unwanted reflections can be caused by a whole bunch of different things, which I'll talk about in a few minutes. So signal to noise ratio, that's what we're looking for. If we have a ratio of 1:1 where we've got just as much noise as we have signal, that's not good. Okay, chances are we're going to have a very unreliable measurement device at that point. Pulse amplitude is not always, we can't just increase the signal strength and hope that the signal to noise ratio will get better. It won't. There are other things we need to do to make that better. So again, signal to noise ratio tells us what's the difference between our desired signal and our unwanted noise. So again, like I said, if the amplitude of the noise approaches the level signal, we're going to lose accuracy. Also, it could result in a loss of signal. With a device, when there's a lot of extraneous noise within there, that's exactly what will happen. All of a sudden, the device is no longer registering your level. You're not getting a good measurement, and you look at an error code, and the error code will say loss of signal or something to that effect. So what causes unwanted reflections, okay, or noise? Well, a lot of things. The cable connectors, if they're not the proper type, the probe connector itself, the probe itself, if we didn't use the right type of probe and we have some impedance discontinuity within the vessel, um, obstructions within the vessel, all of these devices can re-reflect any of these bad signals. And things just start bouncing, right? So a signal gets reflected, bounces off another device like an agitator or maybe a ladder that's in there, and it gets re-reflected. If you've ever accidentally put something with aluminum foil in your microwave and turned it on, you'll know exactly what I mean by re-reflected. These are the kind of things we're talking about here. So how do we avoid problems? Majority of the problems when it comes to radar level devices is improper installation, not following the manufacturer's guidelines, not selecting the right probe. Right there, that probably covers about 98% of your problems right there. Sometimes if we simply can't avoid agitators, or if there's just way too much turbulence within the vessel, we may need to install a stilling well and have the device installed within that stilling well. Improper grounding can also cause a lot of noise. Also, using high quality cabling. People will spend good money for a radar level device, and then instead of getting a good quality shielded cable to make the connection, they'll just grab a piece of bell wire off some roll that's been hanging around in the shop for 20 years and go ahead and wire it up, and then they end up with problems. So with a guided wave radar, we're able to do something that's known as interface measurement. Interface measurement gives us the ability, when we have two liquid materials, or one could be a solid, one could be a liquid, where one is floating on top of the other, and we need to know where that interface between the two materials is. Perhaps we got oil on water, which is a very common one, right? So we've got some kind of a separator system and then oil on top of water. We want to pump out the water, but we want to stop pumping as soon as we get to the oil. Being able to determine that interface with this device, the device can then send a signal to our pumping system and shut it off once we've pumped all the water out and we reach the oil. So there's some basic rules of thumb. Now, these numbers are not cast in stone, but basic rules of thumb. Okay, the dielectric constant of the upper medium, we have to know what it is. Whichever medium is floating on top, we need to know what the dielectric constant is. Okay, and it has to be less than 10. Okay, and it has to be at least 60 millimeters thick. The difference between the upper and lower layer has to be a difference of 10. So if our top layer is 5, our bottom layer has to be at least 15. If there is an emulsion layer, that little layer in the middle where it's neither one nor the other, but there's a little mixture of both, we don't want that emulsion layer to be more than 50 millimeters thick. And again, these are rules of thumb. They're not cast in stone, but they're good rules to apply when we're trying to design a system. So oil on top of water, like I said, is a typical interface measurement application that's done all the time. In this case, we have great separation, right? The oil is going to have somewhere around a dielectric of 2, and the water is going to be somewhere around 80, so no problem there. So what are the pros and cons of guided wave radar? Well, it's a direct level measurement as opposed to differential pressure. Of course, unless you're using tank bottom following, then it's not direct, right? We're interpreting because we're bouncing off the bottom and looking at the speed of the signal. There's no moving parts to wear out. We can use it in relatively small tanks, pretty immune to dust, vapor, and things like that. We can do level and interface measurement, which is a nice plus, and fairly low installation cost. In recent years, these devices have come way down in price compared to what they were 15 years ago, 20 years ago. So they've become way, way more affordable. What are the cons? Well, the probe does have to make contact with the medium that's being measured. That may be an issue in some cases, in which case we may need to look at non-contact radar, which I'll be covering next. Maximum temperature is about 750 degrees Fahrenheit, although now there are some new high pressure, high temperature devices coming onto the market that may actually exceed those temperatures. Heavy foaming applications are always a problem, no matter whether you use this. However, one of the things I will say is that radar is much more forgiving of foam than ultrasonic. If any of you have used ultrasonic in the past, you will know that, any kind of foam in ultrasonic simply didn't work well. Highly viscous materials can coat the probe and interfere with the accuracy of the measurement. If there are agitators and a lot of turbulence, again, we talked about possibly a stilling well would be required to overcome those issues. With guided wave radar, if we're on a plastic or fiberglass tank, we're going to have to make sure we have solid grounding. We're going to have to make sure we use a metal flange so that the signal after it comes back can stop at that metal flange. So that brings us to a series of questions. So what are we actually measuring when we're measuring with a guided wave radar? And I will give you the answer. We're actually measuring the distance from the transmitter to the product surface, okay? And we're looking at the transit time, also known as time of flight, and from that, we're determining where the level is at. Because when we programmed the device, we told it what the full travel distance was, so it's able to basically do some math and figure out where the level's at. Would we prefer a high dielectric or a low dielectric when using guided wave radar? I think I kind of hammered this point home, I hope. And hopefully most of you right away said high dielectric because it will reflect more of the signal back to the receiver and will be easier to read. Which has the higher dielectric, petroleum or water? And again, I did kind of show you a picture of this. I said oil and water was a typical interface measurement application. So the higher dielectric is water. Anything that's aqueous will always have a higher dielectric than a hydrocarbon. Which type of probe will provide the best signal performance for a guided wave radar? And I talked about that a little bit earlier in the presentation. And we mentioned that the best type of probe was the coaxial probe. However, as we said, it may not be suitable for certain applications. Again, corn syrup, things of that nature, you wouldn't want to use a coaxial probe.
Norm?
Yes, sir.
Real quick, we did just have a question come in, and sorry to interrupt you.
No, go ahead.
Regarding grounding, we have a question that says, is solid grounding the base, for example, concrete or steel, or do you mean electrical grounding?
Oh, no, I meant electrical grounding in order to eliminate any kind of noise that could be picked up by the signal. Yeah, okay. We're talking about electrical grounding. Yes, sir. Yep.
All right, thanks. I'll see if there's any follow-up to that. Thank you.
Nope, no problem. Next question is, what is meant by signal to noise ratio when discussing guided wave radars? And again, we talked about this a little bit. And the signal to noise ratio is basically the ratio between the measurement we want and anything else that is not the measurement we want, basically. So unwanted reflections, things like that. What causes unwanted reflections? I mentioned a few of them within the presentation. I may have a few more here. All kinds of things, right? Bad connections, substandard cabling, obstructions within the vessel, reflection of the signal. If there's a lot of rippling on the surface, a lot of agitation, all of that can give us unwanted reflections and contribute to noise within our signal. When doing an interface measurement, what should the dielectric of the top layer product be? Now, I didn't give a specific number on this, but I said it had to be less than a certain number, if you remember. And that number, if you all remember, it should be below 10. The top layer of what we're trying to measure when we're doing interface, we want that top layer to have a dielectric constant below 10, and we'd like it to remain constant. In other words, not fluctuate with temperature, etc. How much separation in dielectric value should there be between the top and bottom layers of the products being measured? And again, we talked about this, and again, it's 10 again. If there should be a difference in dielectric constant of at least 10. So if the top layer is 5, we'd want the bottom layer to be at least 15 or better, okay? Now, there are some guided wave radar products available that are capable of doing reverse interface measurement. So that is something to bear in mind. Not all guided wave radars can do this, but there are some devices that can do reverse interface measurement. in which case if the lower dielectric is the one on the bottom and the higher dielectric is the one on the top, which would be pretty unusual, but that could happen with certain chemicals and things. There are devices that can do reverse interface, and basically it's going to look at the slowdown in signal, etc., just kind of like tank bottom following a little bit. Okay, so that covered guided wave radar, which is guided wave radar, time domain reflectometry, and it is a contact-based radar level measurement system because there is a probe or a cable that has to come in contact with the medium being measured. Now we're going to switch over to what we call non-contact radar. Some people call this free air radar, okay? And there's basically two different methods of doing non-contact radar. There's something called pulse radar, which works very much like guided wave. We send out a pulse, we wait for it to be reflected, we look at the time of flight, and we calculate the level. And then there's something called FMCW, or frequency modulated continuous wave. With this type of technology, we send continuous signal, but as we're sending the signals, we're modulating the frequency. So we're not only looking at the amount of time, but we're also looking at the shift in frequency. This is a superior way of doing things because there's less chance of having a loss of signal. And also, if it's a very long measurement, again, there's less chance of introducing a lot of noise if we're doing this constant signal. So we'll talk about both a little bit. So the measurement principle, right? So James Maxwell in 1865 had this theory about propagation of electromagnetic waves. In 1867, Heinrich Hertz did some experiments and confirmed Maxwell's theory. And then Christian Hutzmeier in 1904 invented something called the telemobiloscope. And with this, he was able to detect the presence of objects. Okay, so he was sending out a radar type signal. He was able to detect the presence of objects, but he was not able to calculate the actual distance. He just knew they were there. He didn't know how far away they were. 1935, GEMA, construction of the first reconnaissance radar. And GEMA is an acronym of the companies that work together working on this. And I forget what the names of the actual companies are, but that's an acronym of their names. Now, the one we're probably all most familiar with is starting around 1960, it became much more difficult to get away with speeding because all the police started having these little radar devices that they could measure our speed and issue traffic tickets. 1976, the first radar level device, but they were very, very expensive then. So they were only used in very large tanks, primarily in the oil industry. They were the only ones who could afford them. 1989, the first what we call compact, meaning, and you know, what we have now. Now, the ones we have now are probably a little bit smaller, but the first compact radar level transmitters, 1989 for process tanks. They were still pretty expensive then, but that was the technology, and they've come way down in price since then. So again, dielectric constant still comes into play, just like it did with guided wave radar. It's also very, very important with non-contact radar because that dielectric constant of the medium that we're measuring is going to determine how much reflectivity we get from the surface of the material. Okay, the amplitude of the reflection isn't quite as important, but we need to get a solid reflection in order to be able to determine. So the 3 Ds of radar measurement: dielectric, right? We want to make sure the process medium is within the instrument specifications as far as dielectric value. Distance, we want to make sure that we pick the proper instrument for the range that we're trying to measure because there are instruments available that can measure different ranges. Disturbances, anything that can attenuate or disturb the signal must be taken into account. Foam, surface ripple or waves, baffles, ladders, agitators, anything else that may be within that vessel can cause a disturbance, can cause some reflections that we don't want and contribute to noise. So first way of doing non-contact is by using pulse radar. And this was used very early on by some companies, okay? And again, it's time of flight. We send a pulse, we wait for it to come back, we determine the time of flight, and from that, we do some math and figure out where the level is. So these are short pulses, okay? and they're transmitted, and the transit time is measured. The pulse duration, the carrier frequency is going to vary by manufacturer, etc. Okay, and there is a time delay between the pulses. And when we say relatively long, well, relatively based on electronics, right? If it's a millisecond pulse, there may be a 5 millisecond, delay in between, or 10 millisecond. That's what we mean by long in this case. So the function of pulse radar, you notice we send a signal down, we wait for it to come back. If you're watching the bottom right side of the screen here, okay. So the transit time of the pulse is used to determine the level. Again, a 1 nanosecond pulse, roughly 30 centimeters, okay. We can get a pretty high dynamic range with these devices, and dynamic range is the ratio of the weakest to the strongest usable signal. If you were looking at a flow device, you might kind of relate this to turn down ratio, okay? Except we don't call it turn down ratio here, we call it the dynamic range of the instrument. We can get a pretty high dynamic range, a spread of about 100 decibels. Now, pulse radar, again, long transit time, you notice there, because there's not a whole lot of fluid. As the tank fills up, we have a short transit time. Okay, so, pretty obvious to see what's going on there, okay. That brings us to the other method of doing non-contact radar, and that is FMCW, or frequency modulated continuous wave. So just as the name implies, we continuously send signals and we modulate the frequency within a range. The shift in that range, the wider that shift in range is, the better we're going to be able to determine, or more accurately determine, the level. So in other words, let's suppose I had a 30 gigahertz device and I was modulating between 29 and 31 gigahertz, as opposed to one that would modulate between, say, 27 and 32 gigahertz. The one with the wider range would actually be able to give me a better quality measurement. So frequency difference between the received signal and transmit signals increases with delay and hence with distance. So we're not only looking at the time, we're also looking at the shift in frequency. We're looking at both things to determine where our level is at. The range to the target is proportional to the frequency difference. Sometimes this is also referred to as the beat frequency. So frequency modulated continuous wave, a linear frequency modulated continuous wave. So you'll notice here, continuous, right? But what's happening is we are shifting the frequency, and we're looking for that frequency shift. And again, the bandwidth of the frequency modulation, how wide that range of modulation is, will affect our resolution. The wider the bandwidth, the higher the resolution we're able to obtain with that device. So again, if we look at this, we have a high level there. So if we have a high level, so notice we're looking at the frequency shift, delta F, and we're looking at also the time, delta T. And with both of those, we're able to get a very accurate measurement, and we're able to do it much better than we can with pulse radar. And now when the tank is low, you'll simply notice that there's a higher shift in both the frequency and the time. And again, this is just another way of looking at the same information with the level high and the level low. So with the low level, wider shift between the two, high level, narrower shift. Now, with just as the probe that we used was important with guided wave radar, with non-contact radar, we have what we call an antenna. Antenna selection becomes very important here, okay? If we are trying to achieve a successful installation, we have to choose the correct antenna for the application. Antennas come in a wide range of shapes and sizes. They are both metallic and non-metallic, okay? The size of the antenna will vary. The operating frequency of the radar device is going to determine. Lower frequency devices require larger antennas. Higher frequency devices can use smaller antennas. So basic information that we need if we're going to properly select the correct antenna for our application. What's the atmosphere inside the vessel, corrosive or non-corrosive? That will determine the material of the antenna. What are the minimum maximum temperatures? Again, that will determine the material. Is this a pressurized vessel? What's the distance, the size of the antenna, etc., the shape of the antenna? Distance will help us choose the right one there. What size is the process connection? That's important too. So we've got a tank and they've got a process connection that's 4 inches. Well, obviously we can't use a 6-inch diameter antenna. It's just not going to fit through that hole, right? Also, is there a nozzle up on top? Are we going to be mounting this flush on top of the vessel or on top of a nozzle on the vessel? And if there is a nozzle, we need to know the length of that nozzle because we may require an extension for our antenna in order to get it at the level where it needs to be in order to properly measure. Some different antenna types. Polypropylene horn antenna. This is a teardrop antenna. Can be polypropylene or PTFE. There's a PTFE horn. This is a flush antenna on a higher frequency device made of a material called PEEK. Also antennas, again, you'll notice extensions here. I mentioned that, depending on where we're mounting this, if there is a nozzle on top of that tank, we may need to add 1 or 2 extensions to the antenna to get it down where it needs to be. Antenna types, metallic. Depending on different manufacturers, you're going to see all types, from one that looks like a flying saucer to one that looks like an ice cream cone, etc. So IEEE, Institute of Electrical and Electronics Engineers, we're going to talk about frequency. So what they have done is they have divided ranges of frequency into bands. And this is just a little chart that shows some of those bands. And frequency is going to have a big effect on the type of non-contact radar device that we choose. So we basically have 3 groups that we separate our non-contact radar devices in: the low frequency range, the mid frequency, and the high frequency. Low, 6 to 10 gigahertz, operates within the CH and X bands. 24 to 29 operates in the K band. 75 to 85 operates in the W band. So what are the pros and cons of each frequency group? Okay, and remember now, antennas and all that stuff will also affect this, but this is just some basic pros and cons. So if we're looking at our lower frequency non-contact radar devices, when it comes to condensation, foam, vapor, and dust, they're the ones that are going to have the least amount of problems with that. Okay, depending upon the antenna type, they may also have the least amount of problems with buildup on the antenna. These are the ones that are least affected by waves or ripples. They tend to have a larger beam, so they will average out those waves or ripples much better than something with a narrower beam, which would be a higher frequency device. It's easy to tune out obstacles such as baffles and agitators. And by that, basically, it's when setting up the device within the electronics, there's something called a snapshot, or sometimes called an empty tank spectrum, where you basically take a picture of it. It's not an actual photo, but electronically the device looks at the empty tank and sees what's there. And what you're saying is, okay, anything that you don't see right now we'll consider to be the level. Okay, and we're able to tune out things like baffles and agitators. And that's more easily done with a lower frequency device. Some of the cons, they do require larger antennas. So again, going back to that example I had before, where maybe the process connection is 4 inches, and we look at a low frequency device and it's going to require a 6-inch diameter antenna, we're not going to be able to use that device for this application. We're going to have to go to a different device. Low frequency devices, though, do have a problem with measuring short ranges. So if we have a very short range, we're going to have to go to a higher frequency device. In the mid frequency, we still have pretty good reliability when it comes to condensation, foam, vapor, dust. We're still pretty good with buildup. Of course, here in the mid frequencies, we can use something like the teardrop antenna. Teardrop antennas are pretty much immune to buildup, whether that be used on a powder or solid, or whether it be on a liquid application, which is a lot of condensation. We still get pretty good reliability when it comes to tuning out waves and ripples. We can still tune out obstacles such as baffles. But one big advantage is we're able to use smaller antennas than the lower frequency at this point. Not good with dense foam. And again, dense foam is an issue no matter what you use, okay? But the lower frequency will probably handle that dense foam a little bit better. Vapors such as anhydrous ammonia could be an issue here. So when we get into the higher frequency devices, okay, anywhere from 75 to 85 gigahertz devices, now the beam is much narrower. So now we may not have to tune out those baffles or agitators. We may be able to just avoid them altogether because we've got a narrower beam. We have very small antennas. So now we can do a flush mount. If we can use, much smaller, to fit into nozzles and stuff. Also, the higher frequency can measure shorter ranges. So if we do have a short range, this is going to be a better choice. Again, shorter blocking distances. So we also have something, and this is something I didn't mention before, but with when we were talking about guided wave radar earlier, there is kind of a dead zone, not only at the top, but also at the bottom on a guided wave radar. Okay, it could be 3 inches, 4 inches, depending. But there'll be an area where, if the liquid or the medium gets within that range, the instrument will not properly measure, known as a dead zone or blocking distance. In non-contact radar, we don't have one at the bottom, but we still have a dead zone at the top. The higher frequency devices allow for a shorter blocking distance, whereas a lower frequency device, you might say you can only measure up to within, say, 10 inches of the face of the antenna or the device. Whereas with a higher frequency, you might be able to get within 1.5 inches or something like that. And again, those are just arbitrary numbers I'm throwing out. So some of the cons. Well, that narrow beam, if you do have obstacles that you can't avoid and you're trying to tune them out, it's going to be more difficult with a higher frequency device. It's also going to be more difficult to, it's going to be more affected by waves and ripples because again, it's just a narrower beam and it's not averaging out across the widest surface of that liquid. It's going to be a little more sensitive to foam and vapor and things like that. But still, these units do work very well in a whole slew of applications. Again, there are some small areas where you want to go to the lower frequency device instead of this. So what are the pros and cons of non-contact radar? Well, just like guided wave, it's a direct level measurement as opposed to differential pressure or something like that. No moving parts, unaffected by density, viscosity, etc. With DP, if you put a different material in that tank that has a different density, you're going to have to retune that whole thing because it's not going to give you an accurate reading. Still fairly immune to dust, vapor, things like that, and we do get very high accuracy readings. What are the cons? Well, if you got an odd shaped tank, it may get a little bit tricky to install a non-contact radar. I'm not saying it can't be done, but you're going to spend a little bit more time. You might have to play a few tricks. You might have to use an angled flange to aim the device so it's not aiming straight down, etc. We do have to consider the dead zone. Okay, may or may not be an issue. May not work well in heavy foaming applications, and surface turbulence could be an issue, again, depending on which frequency device we're using. So FMCW versus pulse radar, okay? FMCW provides the highest resolution. It's better at measuring short distances than pulse, has a better signal to noise ratio than pulse, up to 30 times better. Pulse does have a longer measurement range. That's kind of arbitrary though, because FMCW can go a pretty fair distance as well. Pulse, generally lower in cost, but I'm not sure that that's 100% true anymore. When FMCW devices first came onto the market, they were more expensive than the pulse radar devices, but in recent years, they've pretty much balanced out. So again, they're getting closer and closer in price, and FMCW gives you much better performance. So even if it was a couple dollars more, it would be worth it. Which brings us to some more questions. So what is actually being measured by the non-contact radar device? And of course, you guessed it, the same exact thing that was being measured by our guided wave, the distance from the transmitter to the product surface. That's what we're really measuring. We're looking at either a transit time pulse or we're looking at a shift in frequency, depending on whether it's pulse radar or FMCW. Is a high dielectric or a low dielectric preferred when using non-contact radar? And again, same answer as we had for the guided wave radar. High dielectric will reflect more of the signal and will make it easier to read where the level is at. So there's no magic there, no surprises. This one, the 3Ds of radar level measurement. Give you a second just to think about that while I take a sip of water. And if you remember the 3Ds, it was dielectric, distance, and disturbances. We want to make sure the dielectric is high enough to give us proper reflection. We want to make sure the distance that we're trying to measure is compatible with the device that we're using. And we want to know what disturbances there are that will cause unwanted reflections. What is meant by time of flight when referring to pulse radars? So again, with a pulse radar, this is where we send a pulse, wait for it to come back, right? So the length of time that it takes for that signal to travel from the transceiver to the medium surface and back again. So one complete trip, right? One complete round trip, that's what we call our time of flight. For FMCW, does the bandwidth of the modulation affect accuracy? I did talk a little bit about this. Well, the short answer is yes, but if we want to explain the answer, a modulation of 3 to 4 gigahertz will provide higher accuracy than a modulation of 1 gigahertz. So as I said, it's an 80 gigahertz unit and we're modulating between 78 and 82. That's going to be more accurate than modulating between 79 and 81. Which device will allow the use of smaller antennas, 10 gigahertz unit or an 80 gigahertz unit? And again, we talked about the effect of frequency. And the effective frequency, one of the effects is that as we go up in frequency, it allows us to use smaller antennas. So the higher frequency unit, we can use smaller antennas and hopefully pick up some applications that we were not able to do with the lower frequency units. Which can better handle surface disturbances of the medium being measured, 6 gigahertz unit or 78 gigahertz unit? We talked about ripple or waves on the product surface. That is more easily attenuated by a lower frequency device, okay? Which combination of frequency and antenna allows for shorter dead zones? And again, that dead zone is that little bit of area up there in the top where, you know, if the fluid or the medium gets too close, we basically stop measuring at that point. And we mentioned that higher frequency units can use a lens antenna, right, which is a shorter antenna. Thereby, that allows us to have shorter dead zones. And with that, are there any other questions?
Thanks, Norm. Yeah, as I just turn this screen back over to Kevin quickly, there are currently no questions at the moment, but I will reiterate to everyone that we'll be hanging out for another couple of minutes here. So if there's anything else that's on your mind that you want to get answered, please do send it into that questions panel. If not, you can always follow up with us after the fact, and we'll make sure to get those answers for you. So, Kevin.
Yeah, well, thank you again, Norm. Really appreciate it. And the fact that Marty didn't chime in either means that you did such a great job of explaining everything, or I offended him at the front end of this. So certainly.
Oh, I don't think so. Doesn't that red nose actually raise a lot of money for kids now?
I think so.
Isn't there some charity group? I feel honored. I feel honored.
You should.
But I just looked at what I sent you yesterday, Kevin, and I thought, that's what he pulled out of the bio? Okay, yeah. Fair enough.
Started it. So
careful how far you tip your hand with this guy, folks. Just kidding you. No, great job. Yep. Great job, Norm. I was once again duly impressed, and I think that's it's what I would refer to. I sold ultrasonics for years, And when radar came along, the first radar units we had, you actually had to rebuild the top of the tanks because they were about the weight of an engine block. So I think we've seen some great improvements in this technology over the years. And I refer to radar as what ultrasonics would be if ultrasonics ever grew up. But that's just my 2 cents on this technology.
Very good. We do appreciate you guys being here with it. Certainly, if we have any follow-up questions, we'll get them over to you and get them answered. And again, I would like to take this just a second to announce next week's training. It will be, we'll have two actually next week. We have so many of our OEM customers and packagers and skid builders and engineering customers have asked us over the years about Canadian registration, and we are quite involved in getting parts and pieces to our customers for CRN. So we are going to be having an expert from Pressure Vessel Engineering up in Waterloo, Ontario join us next week. And again, it will most likely be more geared towards equipment builders that are building equipment for destined for Canada. So we'll also, we're working with OPW again for something in the area of dry connect and breakaway, fluid containment, and the evolution of couplings, making sure that we're using the right couplings for the right applications based on product and safety. And also, I would like to take just a second. We do have a tailored training section on our website where we can do one-on-one training. We do have an e-learning catalog with plenty of opportunities. So let us know what you're looking for, and we're going to do our best to deliver it to you. And again, always focused on the training, not the selling. So we appreciate your time, everybody. Once again, thank you for being here. And we do hope that you keep on joining us, and it's up to us to keep on getting you coming back. So have a great day. Have a great week. Bye now.
Thank you, everyone.
Thanks.